cards, and the deal is every card has a number and a letter, and that's what I see on the table. Obviously, there's the other side of those cards. What are the cards that I need to turn to verify that this claim is true? At first, I want to turn the minimum number of cards. But really quick, what are the cards that need to be turned to verify that this claim is true? I have to turn what cards? I have to turn the 8 because it says if it's even, like 8, what am I supposed to see on the other side? Vowel, like 8. What's another vowel? E. E. What's not a vowel? Z. Right? Is 8 the only card I need to turn to verify this claim?
Yes.
No. That's the point of this exercise. There is another card that has to be turned to verify the claim. Obviously, everybody sees the 8. Even a 5-year-old kid sees the 8. It's even. So what the claim says, on the other side, you're supposed to see a vowel. There's a trick here. There's another card that has to be turned to verify this claim. Somebody who didn't talk so far in this class, please. I know you, yes. I have to turn the B. Why? If I see on the other side of B what? An even number means the claim is false. Because if there is an even number on the other side of B, on the front of the card, where it's B, it's supposed to be a vowel, but it's not. How many people follow this thing? We need to turn the B card. That has to do with the contrapositive, right? If every even implies a vowel, that's what the claim says. Claim is saying even implies vowel. That is the implication of the claim. But the same claim can be written as contrapositive, which is, how do I make the contrapositive of the statement? Yes?
It is not a vowel, it's not even.
Okay, not vowel means not even. So we need to turn the big card to verify this claim. I should have put this on the quiz for tomorrow, and oh, sorry, somebody told me how to do this.
It's the toilet.
Yeah. There you go. Okay, very good. So quiz tomorrow and Thursday at your recitation. One more thing before I move on. In the recitation paper from last week, there is a problem. I'm going to write it here. Proofs problem 3 that says for every x in Z that's even, there is a y in Z such that, ST means such that, x plus y is prime and y is prime. Anybody went home and looked at this problem? That's what you're supposed to do, right? Take the recitation paper home and do the problems we didn't finish. So that was a little accident. This is an open question. Nobody knows the answer to this problem, right? I posted the answers online to all the recitation questions, even the ones we didn't do in class. So you should make sure you check those answers before tomorrow. Even if you feel like you did everything, it's a good idea to check those answers. This is an open problem number theory. You have to do the Goldbach conjecture. Some people think it's true. There's a lot of research progress recently on it, but I don't think there is yet a definite answer whether this is true or not. So by accident, this is a problem that's so hard no one knows how to solve, okay? Sorry about that. All right. So now we are ready to move on. Clearly we had better lighting in a different day. I don't know what had happened today. The boards are in the dark. We are in the light. That's nice. I can see you. So today we have only one item. number theory. And like I said before, I would strongly encourage you to use the notes that are on the website, not the book. Book is easier, you can do the problems, you get an A, but it doesn't teach you that much math. So, where were we last time? We, I think, start talking about modulo. So let me take a case here, n equal 9. And Z9, of course, is the reminders set at 9. That is 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? Those are the reminders when I integer divide by 9. So my plan would be to write every A in Z as n times a quotient plus a reminder. In this case, that is A is 9 times a quotient plus a reminder, where the reminder is always in Z9. So we, for people who like visual stuff better, we said here's Z9, how it looks visually. There's 0 here, of course, and we have a bunch of ticks. So the ticks are 1, 2, 3, 4, 5, 6, 7, 8. Those are, this is the Z9. And now I can put any integer on this wheel, not just Z9, but any integer mapped somewhere. If I want to go further in the positive side, after 8 comes 9, after 9, 10, 11, 12, 13, 14, 15, 16, 17, I can keep going, 18, 19, 20, 21, 22, 23, 24, 25, 26, I can keep going, 27, 28, so on and so forth. On the negative side, if I want to go left side of 0, I get minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, and I can keep going. Minus 10, minus 11, minus 12, minus, this is minus 4 here, minus 13, minus 14, minus 15, 16, minus 17, keep going to minus 18, right? Minus 19, so on and so forth. And we made an observation that in this modulo arithmetic on Z9, on this wheel, all those things are equivalent here. All these numbers that fall on the same tick on the wheel, they're actually the same. They are, the canonical value is 1, the reminder. Same thing in here. All these values here in Z9 are the same, they are 3. And same thing in here. All these values are who? 7. About here. All these values are? Right. So everybody is integer set, Z, falls somewhere on this wheel, and on a tick they form arithmetic progression of difference 9, right? Minus 18 to minus 9, that's 9, to 0 it's 9, 9, 9, 9, difference of 9. Same thing in here, minus 11 to minus 2, that's 9, 9, 9, 9. So all those ticks are differences of 9. Our first theorem from last time, I should put here, theorem, was that if A has the same reminder as B, we say that's the same as saying n divides A minus B. Or that's the same as saying A minus B is something n times k. We say A minus B is a multiple of n is a divisor. So in other words, if you take any values that have the same reminder modulo 9, for example, modulo 9, like we have in this picture, let's take two reminders. Let's take minus 14 and minus 13 and 14. We say minus 13 is the same as 14 modulo 9, or that's the same as saying 9 must divide their difference. Their difference is minus 13, minus 14. Is that true? 9 divides that difference? Yes, because the difference being minus 13 minus 14 is the same as 9 times what? Negative 3. So this difference, it's a multiple of 9. It's 9 times an integer. When I say k like this without any mentioning of what k is, that means any integer. I don't mean to say which integer. I mean to say there is an integer that does the job. Like in here, I got the integer minus 3, but the value is not important. The important fact is that this difference is 9 times some integer. Doesn't matter which one. Okay? So that's our first theorem. Two values have the same remainder if and only if their difference is a multiple of n. Be careful that those differences are positive and negative values here. I could have this 14 is positive, minus 13 is negative, but I could pick any values on the same tick and make the difference. I'm going to get a multiple of 9 if they are on the same tick. We also talked about operations. Like if I have 22 plus 38 mod 9, I could do this as 60, of course, mod 9, which is what? 6. Because 60 is 9 times plus what? 9 times what's the quotient? 6 plus 6. This is the quotient, and that's a reminder. Now, this is valid as an integer division only if the remainder is in Z9. It's a common mistake. People write this, the equation holds, of course, that's easy to verify, but the remainder must be in this set for that to be an integer division. But I could do this, we said we could do it the other way. I could say this is 22, we take the mod first, mod 9, plus 38 mod 9. And now what's 22 mod 9? 4. What's 38 mod 9? 2. So that's, of course, 6. I show that we can also do the multiplication this way, right? So anybody can tell me like 22 times 38? Somebody with a calculator, perhaps? What is it?
836.
How much?
836.
Okay, and modulo 9. 9 in 81. The quotient in here doesn't matter, right? Because we only need the remainder. So 9 in 81 is 9 times, I get the 2, right? 26. 9 in 26. I get 18. That's an 8. Right? How about in here? 22 modulo 9 is 4 times 2 modulo 9. Those are the same like before, right? So that, of course, is the easier way to do those things is to take the mod as soon as possible, because otherwise you can get big numbers. But if you take the mod early on, you operate with small numbers. We also did another thing which we call fast exponentiation by repeated squaring. So in here we show that if you want to compute some power modulo, you're better off doing erasing by repeated squaring. So for example, suppose I want to do 11 at 42. Actually, let me write this here. 11 at 42. I could do 11 times 11 times 11 42 times. This is mod 9. This is 11 times 11 times 11, 42 times, modulo 9. But that's a slow operation, right? I have to do 42 multiplications. Instead, I could do the powers that I need, the powers of 2 that I need in 42. So if I write it, what are the powers of 2 that I need in 42? 32 plus 8 plus 2. So that is 11 at 32 times 11 at 8 times 11 at 2. I don't say mod all the time. You should, but for me to go faster here, everything is modulo in here. So how do I do that? I need to get first 11 squared, of course. That's 11 times 11. So that's, what's 11 mod 9, first of all? So 11 mod 9, of course, is 2, right? So 11 times 11 will be 4. That is mod 9. And then the next power is 11 fourth, will be 11 square, everything square, which is, I just computed 11 square, that is 4 square mod 9. 4 square is 16, modulo 9 is 7. Next power is 11 at 8, that is 11 at 4 square. I already have 11 at 4, that's 7 square. So 7 square is 49, modulo 9.
4.
4 or 5?
4.
Let's make it clear. 49, which is 4, modulo 9. And then the next power will be 11 at 16, which is 11 at 8 square. I already have 11 at 8, that is 4 square. 4 square is 16, that's 7, like before. And the last one I need is 11 at 32, that is 11 at 16 square. I've already got 11 at 16, which is 7 square. 49, things are repeating now. 49 is 4, modulo 9. Of course, if I keep squaring, 4 will become a 7, and 7 will be a 4, and this pattern is going to repeat. So now I get, what is 11 at 32? 4 times 11 at 8 times 11 at 2 4. We made a mistake here. That's not a 2. 42 is 32 plus 8 plus 2. That's correct. 4 times 4 times 4. So that is how much? That is 64, right? Which is how much modulo 1? Okay. How about the other way? I mean, I could play with this type of arithmetics in a different way if I want to. I could say how much is 11 at 12? I could write 12 as a sum of powers, but I could write this as a difference of power. For example, I could say that's 11 at 16 divided by 11 at 4. Division doesn't always work, but sometimes it works. And in here, so I should put some question marks because division doesn't always work. But if I am to write 11 at 16, what is that?
7.
That's a 7. And 11 at 4 is a
7.
7, right? In this case, can I tell if division works or not? Is there a number that multiplied with 7 gives me 7? Modulo 9? Because that's what it means, the division to work, right? Division is, this can be done, this works, if and only if there is a C such that B times C equal A. Right? That's what division means. If I could get something that multiplied back with B gives me 8, just in the regular algebra, I say division works. It doesn't work all the time. But in his, it's easy to tell if it works or not. Is there a number that multiplied with this 7 gives me the other 7? Yes. Well, the number is 1. So in this case, it worked. That's where we were last time. Right? Oh no, we said one more thing about ciphers. Ciphers have to do with division to make them work. So we talked about linear ciphers. Ciphers do these linear ciphers. They take an original message. I just say ori message, which for us mathematically that's a number. Of course, when we encrypt something, that may not be a number, maybe a piece of text, a password, encryption, whatever. We transform that first into numbers. Actually, computers do that. Whatever I have stored, they're already stored in a numerical format anyway. So when we think mathematically about ciphers, we only think of encryption of a number. So we do the encoding. And the encoding, because it's a linear cipher, it's going to be A times the original message plus B modulo n. N is fixed. So n is fixed and known in advance. In encryption, decryption, n doesn't change. If I do the alphabet, I showed you last time, a good idea for the alphabet would be n to be 26 because there are 26 letters. But you can choose any n you want. So that's the cipher here. This value. And if I'm to decode it, I need to apply the reverse operation. I need to get back the original. That would be the point of decoding the cipher, to get back the original message. Now, that original can be computed. If I look formally at this algebra, what are the reverse operation? Will be take the cipher, subtract. How do I reverse this A times something plus B? I do minus B, and then I divide by A. Okay? If this operation works, I get back my original message. Everybody sees that in regular algebra, this is the exact reverse operation of the encoding. Hands up. Good. Well, if this is modulo, right? If it works. If division works. The thing is, as a function, so in a functional sense, encode takes the original and produces the cipher, which is A times original plus B. That's the cipher. And the decode takes the cipher and produces cipher minus B by A more than. This is more than. Which should be the original. This works if, so minus B always works. We don't have to worry about this minus B. To everything that I add a bunch of ticks on the wheel, I can take them back, no matter what the B is. B could be 100, 1,000 on this wheel. If I move 100 ticks one way, I can move 100 ticks the other way, no problem. But this is a big thing. That's our purpose for today's lecture. Divide by A, 1 over A does not always work. So that's the thing with the minus. Always we can bring in minus, no problem. We don't have to worry about that. You can choose any B, it's going to be fine. But A does not always work for division. So when it does, we say A has a multiplicative inverse. And we call it A at minus 1. Again, not everyone has an inverse modulo n. Some numbers do, Some numbers don't. This minus b, sometimes it's called, very unfortunately by the book, really please don't use this word, additive inverse. I really don't like the word inverse, so I'm going to call it opposite or something like that, because I want to reserve the word inverse for multiplicative inverse. Every time I say inverse, I mean multiplicative inverse. Of course, when it exists. As I said, not all the time we have a multiplicative inverse. Now the book calls additive inverse the minus b. So minus b is the additive inverse of b. I don't like that word, but if you see it, there's an inverse to the operation of addition, that's minus b, always works. And there's an inverse of the multiplication operation, which is a at minus 1, does not always work. Are we making progress with that attendance sheet? Where is it? Okay.
Doesn't seem that like it.
Everybody needs this? Okay. So I want to take two cases here. Say I'm now in modulo 26. I like 26 for letters because it allows me to map all the letters one-to-one into a number in Z9. So of course Z26 is from 0, 1 to all the way to 25, right? So here's a cipher. Sometimes instead of using the variable original, we call the original x and the cipher, we call it y, to make it look more mathematical. That's okay as long as you're very clear who's y and who's x, not get confused with is x the cipher or is x the message or what is x. You got to be very clear what it is. But once you are like me here, I'm not going to call it cipher original in equations. I'm just going to say the original is x, the cipher is y. So here's one case. I have here a equal 5 and b equal 11. So my equation is the encode is going to be what? Y, the cipher, is who?
5x
Plus 11, right? 5x plus 11.
mod 20.
Mod what?
20.
20. Right? So this is saying the cipher is 5, that's a times the original plus b modulo 26. I just replace x instead of original, a is 5, b is 11. What is the decode operation? I need it backwards, right? I get a cipher, I need to get out the original message. So that will be x equal y minus 11. From now on, we're not going to use this notation, but that's correct. There's nothing wrong with it. I like better this notation. So how do I say that? Y minus 11 times 5 at minus 1, right? That is to say here, this is the cipher minus b times a at minus 1. That would be the original. Of course, this is if. There's a big if here. If what? What do I need for these decode operations to work?
5 to have a multiplication.
I need 5 to have a multiplicative inverse. How do I say that mathematically? If there exists what? 5 at minus 1, right? I need 5 at minus 1 to exist.
Mod 20.
Mod, of course. Everything is mod 26. Once you fix the n, 26, everything is mod 26. Now, what does that mean? Let's actually work on this. What does 5 minus 1 exist? It means there is some value, let's call it b minus 1. What property needs to have to be the inverse of 5?
The mod needs to equal 1.
What?
The mod needs to equal 1.
when I do what? You're right, I need to get mod 1 when? What's the property of this value to be called the inverse of 5? Multiplicative with 5 has to give me 1. So this has to be a b minus 1 value in, this is z26, so it's got to be one of those values in z26. That when I multiply with 5, I get 1. Is there such value in z26 that when you multiply with 5, you get 1? Anybody knows a value? By the way, if exists, is unique. So you don't have to worry, oh, my friend found an inverse. Can I find a different inverse? You don't have to worry about that. When the inverse exists, there's only one. So if you find one, that's the one. Okay? Anybody knows a value in Z26 that when I multiply with 5, I get 1?
Is it 0?
0 times 5 is what?
Oh, 0.
Okay.
Oh, sorry, negative 1.
Is there any value that when I multiply with 5, I get modulo 1? 21? Huh. How about b at minus 1 is 21? Because 21 times 5 is 105. How much is 105 modulo 26? 4 times 26 is what? 105. To get this, we get it 26 times 4 plus what? Plus 1. So this 1 means it's 1 modulo 26, right? Because 26 times 4 modulo 26 is 0. So somebody found it. 21. 21 works. Because when I multiply with 5, I get 1. So when it exists, is unique. Again, you don't have to worry about there may be 2 or 3 inverses, and I found one, and he found a different one. You know, if you find a different inverse than your friend, one of you is wrong. There's only one inverse. Now, that's not always an inverse, so sometimes there is no inverse, but if there is, it's unique. Everybody understood how this goes? Question?
What about negative 5?
Negative 5, you're asking if negative 5 has an inverse, or
No,
if
no,
it's...
if negative 5 is the inverse for 5, because it gives you
It
negative
is.
5.
Why is negative 5 the inverse? He's saying, hey, I found another one. How about this other value, this b minus 1 prime minus 5? Isn't this an inverse to 5? Is it an inverse or not?
Yes, I know.
It's just not in the set.
Hmm?
It's not in the set. It's not in 0 to 26.
First of all, it's not in 0 to 26, 25. But where is minus 5 on this wheel here?
21.
Minus 5 is the same as 21. Right? In modulo Z26, minus 5 and 21 are the same thing because their difference is 26.
So only one inverse can exist.
Only one inverse in here. Of course, any other value that's on the same tick with the inverse will act like the inverse.
Yeah.
But as the canonical ticks from 0 to 25, there's only one in Z26.
You said like what value of b times 5 equal 1 not 36. But how come it's b to the negative 1?
There's just a notation. So let's just say inverse. Inverse of A.
Okay, so
That's wrong, of course. B was this 11. You're right. So it's not related to B. We were looking here for the inverse of 5. And that's a value that when we multiply with 5 has to give me 1. Somebody proposed 21 as the inverse. We multiplication. We get 1.
So 25 is b to the negative
25 is what?
1. Is b to the negative 1?
How much to negative 1?
No, b to the negative 1.
B is 11 here.
So like at when you said
This is 5.
minus 5.
Sorry.
Oh.
5 and minus 1 times 5. Okay, so let's go back and fix the notes. Whoever thinks this is B, that's
It's actually A.
what?
Like you can write it in the general form as A, right? Because you already know.
Right. But we don't care about this 11 for multiplicative inverse. We care about the A. In a linear cipher, A is the killer. A has to have a multiplicative inverse, and A is 5 in here. So 5 at minus 1 exists because there is a value. We say that's 21, right? 21 times 5 gives me 1. Now, how about the different example? Still modulo 26, but I'm going to use a different A and B. Actually, I can write it right here. So a different example, I'm going to use A equal 4 and B equal 3. So if I pick those A and B, there's another same A and B out in here. I'm going to have Y, the cipher, is 4x plus 3. This x is the original. And the other way, if I want to get out, this is decode operation. How do I get x out of that? I would need to say y minus 3, reverse the addition, but then multiply with what?
4
The inverse of 4. Everything is modulo 26. Of course, this works if and only if there is an inverse of 4. Modulo 26. So this is equivalent to what? If two numbers, so let's write it again, x equal with 4 at minus 1 times y, right? Minus 4 at minus 1 times 3. That's what I would need. So now if I multiply everything with 4, this is modulo 26. If I multiply everything with 4, I get 4x should be y minus 3. Right? Modulo 26. Why is this not, is this possible or not?
No.
No. Why is not possible?
4
Why
times 6.
4 at minus 1 does not exist? So the conclusion here is going to be 4 at minus 1 does not exist. Modulo 26. So this cipher would not work because 4, which is my A in there, has no inverse that I could use.
Wait, how do we know that?
Right, that's what I'm asking you guys. How do we know that this works? I mean, we know this works because we tried values and we found an inverse, right? We could try all values and see if there's an inverse. But in here, how do we know there's no inverse? We could do the same, try all the values and find no value. Before, I'm going to let you speak or ask the question. But what would it mean to be an inverse? If there is an inverse, what is the definition of an inverse? What the property inverse needs to have? 4 at minus 1 multiply with 4 has to be 1 modulo 26. And there was a theorem here that says if two values have the same remainder, then what?
Then we're on the same view.
That the theorem says something very specific.
Then the difference can be divided by n.
The difference 4 minus 1 times 4 minus 1 is a multiple of 26. That's what the theorem says. If two numbers have the same remainder, their difference have to be a multiple of 26. Now, yes.
I was just gonna say that 4 is even, so it's 26.
So that's correct. The observation is this number is even. Always. No matter what the k is, 26 times k is going to be an even number. 4 times something also going to be even. Remember, 4 at minus 1 has to be an integer. It's not 0.25. In here, there is no 0.25. This 4 at minus 1 is an integer. So 4 times an integer, isn't that an even number? Even. Right? Who's with me? We all understand why 26 times something is even, I hope. How about 4 times some 4 at minus 1? 4 at minus 1 is, has to be an integer in Z10. Everything in here is in Z10. So it's got to be one of these values if it exists. Don't confuse it with 1 over 4, which in real numbers is 0.25. That's not the one. If this is an integer, then this value here is even. And this being even, this is immediately an impossibility, because if I subtract 2 even numbers, I can't get 1 as a difference. Right? We all see that? The difference between 2 even integers cannot be 1. That's why it doesn't work. In a more general sense, it doesn't work because 4 and 26 share common factors. General. 4 and 26 share common factors. In this case, what's the factor that we were looking at? 2. Why would you say p equal 2 is this factor? That's common between 26 and 4. Every time they share a factor, any factor, 2, 3, 5, 7, doesn't matter. They cannot have an inverse for that reason. Now, that's a beautiful story, but we need to make it more mathematical. So now that we have a story in our minds, we have to study those problems. And in the notes, you'll see every once in a while, a result is marked with a white on black text. Those results are the ones we truly need to do cryptography. Those marked like this. The others are the mathematical that's necessary to get to those results and prove them. Right? So there's a lot of other small lemmas and theorems and results that we needed to get to those bold ones. And those bold ones is what allow cryptography to work. So we're not only going to solve linear ciphers, but we're going to talk about a different kind of cipher that's actually good in practice. Linear ciphers will be easy to break, no matter how big the numbers is, N, A, B, so on and so forth. It'll be quite easy to find A and B and break it. But there's other ciphers who are hard to break.
Is there any practical use for linear cipher?
What?
Is there any practical use for linear cipher? Like any programs to that? Or not really?
Yeah, there's many programs that you can use. In fact, I'm going to show you one today written by us. But there's efficient, that's what you mean. There's, very efficient operations. But the bits on those cryptography values like N, A, B, those things will be gigantic, enormous numbers. Things that have 600 to 800 digits. Okay? So you need efficient operations. You can't just do multiplication or exponentiation normally, because that will be very, very slow. All the operations on huge numbers have to be extremely efficiently implemented to be practical. So we're going to get there, but before we do, we need mathematics. So we're going to start building a number theory.
Do we need to know how to prove the theorem?
I expect informal proofs. So I expect you guys to not necessarily do formal proofs, but to be able to follow in this kind of reasoning, which is in the notes, and I'll do it in class. If I say something's optional, then that means it's not expected. But while we don't grade formality, how well mathematically you wrote things, the argument, the logic has to be correct. So the first things we do is primes. We know the set of prime numbers, right? 2, 3, 5. What's the next one? 17, 19, 23, so on and so forth. This value P prime means P has no proper factors. By proper I mean other than 1 and P. Of course any number will divide by 1 and by itself, but prime numbers do not divide by anything else. I'm sure we all know that. And so our first job is primes and factorization. The thing is, any number has unique factorization into primes. I'm pretty sure you've seen this before in high school at some point. So let's say that I mean something like P1 times P2 times P3 times some Pk. But if a prime repeats itself, we don't write it 2 or 3 times. We write it with an exponent. So all these exponents have to be at least 1. So if P1 is the prime 3, but there's more than 1 3, 3 times 3 times 3, then that's going to be 3 at the power of 3. So as an example, what about 12? 12 is 2 times 2 times 3. How do I write that? 2 squared times 3. And if I read it in number theoretic, it's 2 2's, 1, 3. 2 comes from this exponent. There are 2 2's in here. And how many 3's? 1 3. How about 48? That's 2 times 2 times 2 times 2 times 3. So this is 2 to the 4 times 3. So how do I read this? This is 4 2's, 1 3. Yes?
Can you explain the e's again?
The e's are these exponents. 2 to the 4. E1 in here. So if I do this, I effectively said that P1 is 2 and E1 is 4. And in here, the second prime is 3. And what's its exponent? If it has no exponent, what's the exponent? 1. Any integer, positive or negative, can be written uniquely into primes. How about 36? This is 2 to the, let's just write it directly in the concise form. How many 2's are in 36? 2 times
3.
how many 3's?
2 3.
How about 50? Somebody else, 50. 2 times what? 5 squared, right?
Yeah.
Because this is 5 times 5. How about 1452? How many 2's fit in here? Obviously 2 fits at least once. Why? It's an even number. Try to divide by 4, which is going to work. What's the criteria for divisibility with 4? 52 is divisible by 4? Yeah, so it should work at least with 4. How about 8? Let's try to divide by 4. So 2 to the 2, what's the quotient if I divide with 4? 363, right? That's any further divisible 2? No, so there's only 2 2's. Who's following me? There's more 2's in here in this 363 or not? No. Hands up, who's with me? Okay. So how about 363? What do I divide that by? 3 and I get 121. And who's 121?
11.
11 squared. Right? So you can do this for any number, and at recitations, and there's plenty of practice, we'll have more and more exercise about this. The only thing here, a little like you have to pay attention to, I'm sure you understand the mechanism, is values like this 363. Is it prime or not? Maybe it's prime and I don't have to further decompose it, but maybe it's not prime and I just need, or 121. I need to try a few primes to see if I can break it or not. But other than that, this is a relatively easy thing. So now we have another theorem that says prime P, so P is prime, P divides a product implies P divides one of the factors. So when a prime divides a product of things, it's gotta divide one of the factors. For example, if let's take this example here, 11 is prime, right? 11 divides 1452, which, for example, I could write as 12 times 121, right? This is 12 right here. 12 times 121. Because 11 is prime, and this is a product of two things, there must be that prime divides one of them. So in this case, P divides 121. This theorem is not true if P is not prime. So if P not prime, theorem not true. For example, 4 divides 6 times 10. Is that true or not? How much is 6 times 10? Divide by 4? Works, right? The theorem would imply, I'm going to say here TH from theorem, that if 4 divides 60, must divide one of the factors. That's what the theorem says. But of course, theorem is only true for prime numbers. So the implication would be it divides either 6 or, I could write or in English, 4 divides 10. Is that true? Does 4 divides one of the factors here? Is 4 a divisor for 6? No. Is 4 a divisor of 10? No. So this is no, no. The reason is this doesn't work. Because P, in this case, 4, is not a prime number. This theorem works, but only when P is prime. Now, why does it work? We can't make this proof formal, and it's not our job here to make it formal, but why is that true? Why, if a prime divides a product, must divide one of the factors? So the proof, whenever I write a bad proof, like a not formal proof, not mathematical proof, to hide the fact that it's not so good, I'm going to say proof idea or proof sketch. As in, I have the right idea, but I really don't know how to make the proof mathematically. Sometimes that's okay in computer science. We have the right idea and we understand the mechanism, but we don't know how to write it formally. That's much better than having no clue how to prove the thing. Here's what I'm going to say. A times B has a factorization. Any number has a factorization. Let's say that factorization is some P1 at E1 times P2 at E2 times Pk at E2. Right? There's a bunch of prime numbers with exponents that give me A or B. Now, P divides the product, and P is prime. I say P must be one of those prime factors. The only primes that divide this product are the primes that are in the product. If a prime, like for example 11, is not part of this product, 11 will not divide the product, right? The primes that's going to divide this are the primes you see. And every other divisor of this is the combination of those primes. Now, because AB has this factorization, every single prime has to come either from A or from B. How do I get this product? If P1 is 3 at the power of 7, that means there are 7 trees. To get 7 trees, some of them must come from A and some of them must come from B, right? So every Pi must come from either A or B. The reason I get any prime in this factorization is because it belongs to A or B. Now from these two things, it means P, because P is one of those primes, P is either in factorization of A or in factorization of B. Because all the primes are either in A or B, and P must be one of them, so it's either in A or B, which would imply P divides the number it comes from, either A or B. Now that's not a rigorous proof, but it's the right idea for a proof. Some things we can't do formally because we need axiomatic mathematics and things like that we don't want to get in. So we've got factorization to work. And we have this nice theorem here. There is another side of this theorem, which I'm going to leave it as an exercise for you to think about. So it's the same theorem, kind of version B, that says if prime P, so I have primes P and Q, two primes, they divide, but they are different. They divide the same value, then their product divides that value. So if two primes divide a number, their product also divides that number. So for example, let's take one example here. For example, 50. 2 divides 50. 5 divides 50. Right? That's two primes, P and Q. That's my P, that's my Q. And P and Q are different primes. They're not the same, and they're both primes. Is that true? 2 and 5 are primes? Right? My theorem in here, theorem part B, says what? In that case, the product of those two primes must divide 50. So 2 times 5 divides 50. Everybody understands this notation, divides? Divides. It says some number, say P, divides A. That's the same thing as saying A is a multiple of P, which is the same thing as saying P is A times K. Those three things mean the same exact thing. P divides A is a multiple of P. Backward. PK. So A is P times K. Okay. So we introduce the primes and the factorization into primes. And what we need to do next is to introduce one more thing with the primes, which is the GCD. GCD stands for what?
Common factor. Not divider.
Greatest common divisor. So like between two numbers, right? Let's say between A and B. That's between of A and B. Between two numbers. Now that's the name, GCD. You can see how I got the G here and the C and the D, so that's why the whole thing is called GCD. Makes sense syntactically, but what's the definition, the mathematical definition of GCD? That sounds G and C and D, fine, but What is GCD? Can anybody give me the actual definition?
Like the largest number n in which n divides A and n divides B.
That is correct, and the book says it's exactly like that. Right? But we're not gonna do that. It's not wrong, but that's a very bad definition of GCD. If you use that definition, the largest number that does stuff, hard to do any math with it. What is the definition?
If you have numbers A and B, if you have the set of prime factors of A and the set of prime factors for B, where those two sets intersect, and then the product of those factors would be the greatest common divisor.
That's the definition we want. Now, what he said is true. It's the largest integer that divides both of them. But we don't like that as a definition. We like this one, which is definition. If D is the GCD of A and B, that means D is the product of all common prime factors with proper counts. So a prime might be common more than once. If it's common twice or three times, I have to include it twice or three times in the GCD. Let's take an example. 48, we had it there. How many 2's and how many 3's are in 48? 2 to the 4 times
3.
3. How about 36? 2 to the
2.
2 times
3 squared.
3 to the 2. So this is 4 2's and 1 3. This is 2 2's and 2 3's, right? So what's in common? How many 2's are in common? 2 2's are in common, right? Because this guy has 4, this guy has 2. How many are in common? So in common, I have 2 2's, and how many 3's are in common? 1 3. So that would mean what? If I write it now mathematically, 2 at the power of 2, because there are 2 of them, times 1 3. So that is the GCD of 48 and 36. So we can prove that the largest integer that divides both of them is indeed 12. But we're not very interested in that proof. I'm much more interested in you guys avoiding that definition. Okay? So for now, let's pretend we didn't hear it. GCD is not the largest number who divides the things. I mean, it is, but we're going to ignore that fact. We're going to think of GCD how? The common prime factors multiply. And be careful with common means more than one sometimes. In here, there's 2 2's. Another example, how about between 60, what is 60? 2 to the 2 times 3 times 5. How about 50? 2 times 5 squared, we have it there. So what's in common? The GCD of 60 and 50 must be the common primes. How many 2's are in common? 1, 2, and is there any 3 in common? No. But what else is in common? 1, 5. So this gives me 10. How about 8, 9, 1, 8? What is this? This is 2 times, I say here, 7 to the third times 13. I think you can believe me on that. 9800 is 2 to the 3 times 5 squared times 7 squared. Again, please trust me on that. What would be the GCD of those two values? 8918, 9800. How many 2's are in common? 1. How many 5's are in common? None. So I can write 5 to the 0, but I don't want to waste my time. I'm just going to skip the 5 here. What else is in common?
2 7's.
2 7's. So how much is 2 times 7 squared is what? 2 times 49? 98. That is the GCD. That's the GCD we want. Please do not attempt to see what the largest number is by trying possibilities. Get the primes out and see the product of the common primes. That's by far the best way to do it. How about 60, which we already had, 2 to the 2 times 3 to the 5, versus 637, which is 13 times 7 squared. What's the GCD here between those two? 60 and 637? Is there anything in common?
Yeah, one.
Nothing, no prime. 1 is not a prime number. Okay? Prime number starts at 2. So is there any prime in common? When there is no prime, what do we say? We say 1. That means no common prime. How many people have seen this GCD of two numbers being 1 before? Meaning no common primes. Hands up. Okay? So not that many. This is a very important concept for us. Two values. They're not prime themselves. Neither one of them is a prime number, but they have no common factors. So they prime to each other if you want. No common factors or relatively prime. We could say that. Relatively. It's no prime numbers, but relatively prime. Not to be confused with the fact that one of them might be prime. Relatively prime doesn't mean either one of them is prime. It only means they have no common primes between them. So we have an algorithm for finding the GCD. Anybody knows it or heard of it? How do I find the GCD of two numbers in general? I could do this, but this is not practical if I don't know how to factorize the numbers, right? This is extremely fast if I know the factors. But for large numbers, I don't know the factors, and factorization is an expensive process. It takes a lot of computing powers to get factors. We're going to talk about that next week, why factorization is such a complex process. Again, if I know the factors, I get GCD right away, no problem. But only if I know the factors. What if I don't know the factors? GCD without knowing the factors. Anybody knows this algorithm?
Euclid's algorithm?
Euclid. So Euclid made the following observation, which is a theorem. He says, if you want A and B, right? We want the GCD of A and B. GCD of two values. Presumably A is bigger than B, let's say, but it could be B bigger than A, doesn't matter. This is the same as the GCD of A minus B and B. So he made this observation that if you subtract the small one from the big one, so I have two values now, B is the same, but A is not A anymore, it is A minus B, the GCD will be the same. So if that's true, I can repeat this process, GCD of A minus 2B, right? I can keep subtracting B from A, which is GCD of A minus 3B and B, right? If it works the first time, I'm just gonna keep doing it and doing it and doing it. And if I do the integer division, right, this B times Q plus R, let's say B is a positive value for now, so we can do the integer division. And then R has to be in ZB, right? R is the reminder, has to be in ZB. How far can I go with this process? Until when? How many B's can I subtract here until I kind of run out of B's to take out? QB, right? That's the maximum number I can take out is QB and B. So what is this? How much is A minus QB? A minus QB is R. So that is the fundamental property of Euclid algorithm. It says that if you take a bunch of B's out of A, you don't change the GCD. So we can take one at a time, but one at a time is very inefficient. If we know the integer division, we can take all cube B's out of it at a time. So the Euclid algorithm says if you want the GCD of AB, instead, and A is BQ plus R, instead compute GCD of B and R, because that's the same value. According to the theorem, it's the same value. So if my purpose is to get GCD of A and B, Euclid algorithm says do B and R. Of course, what's the advantage? You could say, so I still have to compute the GCD. What has changed from AB to BR?
R smaller.
The values are smaller, right? So these are, BR are smaller than the pair AB, right? So the advantage is not that I still have to do a GCD, but with smaller numbers.
Do we like restrict GCD to positive integer?
No. GCD positive or negatives is the same. You can easily see that GCD of A and B is the same as GCD of minus A and B is the same as GCD of A and minus B, the same as GCD of minus A and minus B. But in GCD, we always take the positive number. So we look at the primes, we ignore the sign, and we take the common primes. Yes?
Could you also just keep going and do the same thing?
Yeah.
with R and then you get
Yeah.
to the small
So now I have this problem, right? GCD of B and R. How am I going to solve this problem? Well, we're going to say, okay, well, B must be R times, let's say, another Q2 now, because I'm dividing it, I get another quotient, plus some sort of R2. This is an integer division with respect to B and R. It's kind of the same like in here, just two different values. So I'm going to say, okay, instead, compute GCD of what are the values that are now B and R for me.
R and R.
This is R and R2, right? Something like that. So in here, this stands for the previous A, this R stands for the previous B, Q is the new quotient, and R is the new remainder, right? So when I move to the B and R, my next B and R be R and R2. And I can keep going with this process, right? I could say now, okay, R is R2 times a new quotient plus a new remainder. So instead, compute the GCD of R2 and R3. And because of the theorem, the GCD is the same value. As soon as I know how to compute it, as soon as one of these things checks out and I say, I know what the GCD is, I'm done. Because that value is the same as this, is the same as that. So this is the same, that's the same. So whenever I get to small enough numbers that I can actually tell what the GCD is, I'm done. So keep going until I get something like GCD between, for example, some R value, K, and 0. What's the GCD between some number and 0?
The number itself.
The number itself. So that would be RK, and that's my answer. I say done. Because I don't have to worry about what the other procedures do. The GCD never changed. As soon as I compute it, that's the one. Before I take questions, I want to show you an example. So how about A equal 22, B equals 6? How do I write this? 22 is 6 times what?
6 times 3 plus
plus 4. So now that's my A, 6 is B, Q is 3, and R is 4. So the GCD tells me to, instead of do GCD of 22 and 6, instead it tells me do GCD of what? B and R, right? 6 and 4. So now I would like you every time to move to the next step of Euclid algorithm to restate the new A. Even if you call it A, mathematically it's not correct because A is 22. When you move to the next line of GCD, I want you to restate who A is, who B is, who Q is, and who R is, right? So in here we have Q equal 3 and R equal 4. Now we move on to 6. B is 4. So 6 is 4 times what? 1 plus 2. So who's Q? 1. And who is R? 2. So we move now into GCD of what?
4 and 2.
4 and 2. So A is 4, B is 2. We say 4 equal 2 times 2 plus 0. So the quotient is 2. Reminder is 0. Every time I get reminder 0, I know who the GCD is immediately. The answer is GCD in this case, because reminder is 0. That's the stop sign. And what's the GCD? Out of A, B, Q, R in the last line. A is 4, B is 2, Q is 2, R is 0. Which one is the GCD?
B.
Q happened to be the GCD, but that's not a value we're looking for. Who is the GCD?
B.
B. Meaning the last B when R was 0. The moment you see R equals 0, the last B you have, this B here, that's the GCD. Because the next GCD, if I were to process further, the next GCD will be between who and who? 2 and 0. And the GCD of that is 2. So there is an intuition of this theorem and this algorithm. The intuition is, suppose I have this suppose I have this grid here. Like I'm a tile worker and I go to somebody's patio and I have to do the patio, right? And this is 22 by 6. So here's a 6, here's another 6, here's another 6, and here's a 4, right? So if I think about this, it's 6, 3 and 3, 3 and 3, that's 4. This is 3. Maybe I get it wrong, but I'm pretty sure you know what 22 by 6 grid is. That's 22 by 6. And I want tiles, square tiles, as big as possible to cover my patio, which is 22 by 6. Question is, what's the biggest tile that I can use to completely cover this up? Right? I could use a 1 by 1 tile, of course, that would be 6 times 22 tiles, but I want to look nice. I want these Italian patios with big tiles, right? Square. What's the biggest tile I can use? The intuition of the theorem says, well, whatever bigger tile you use, maybe it's 2 by 2, maybe it's 3 by 3, maybe it's 4 by 4. When you get the 6 by 6, see, this grid here, 6 by 6, that's going to be covered with those square tiles. Whatever that square tile does, it's going to cover a 6x6 ratio. It has to, because it has to fit evenly within this 6, so evenly within this 6. 22 is the whole thing. This is 6. That's another 6 here. And that's another 6 here. And that's 4. So the theorem says this whole 6x6 will be covered by your tiles, no matter what tile you use, if you do it correctly. This 6x6, it's another when I subtract the 2b, right? So this is now 22 minus 6, that's 18 versus 6. This is not 18, I subtract 6, that is 16, right? So 16, see if I take these tiles out, I have now a 16 by 6 grid. Then I take another 6, that's 10 by 6. I take another 6 by 6 grid out of it. What's the remainder? What's this piece here? Which is this 4 by 6 in here. So the Euclid algorithm is like this masonry guy who tries to put the tiles here and says, I don't know what tile I need, but whatever the biggest tile works on on the whole patio, it's gonna work on 16 by 4. Take the 6 out again, 16 by 6. And then take the 6 out again, it's going to be 10 by 6, 6 by 4. And now I reduce it to this problem. What's the biggest tile that I can use to cover this 6 by 4? We use now repeatedly Euclid. What would be the answer? What the tile I need? 2 by 2. Why? Because the GCD of those two numbers is 2. So the biggest tile is actually 2 by 2. You can see how I can fit these tiles. In there, and then I can fill it the rest. So that's GCD, and we'll have plenty of examples about this. Let me do another one. Try to do it faster. I think most of you have seen GCD before, and the Euclid's algorithm. How about 51 and 9? So A equal 51, B equal 9. 51 is what times 9? 9 times what?
2 plus 9 times 2.
To get 51?
Oh, wait.
9 times 5. That's 45 plus. So I'm going to make a little column here. Who's Q in here? 5. And who's R? So my next GCD will be, what will be my A now? I'm moving from GCD of AB to GCD of who? Of B and R, right? Who's my, so B and R are what? 9 and 6. So A is now 9, B is now 6. 9 is 6 times 1 plus 3. So who's Q? 1. Who's R? 3. So my next line will be GCD of 6 and 3. A is 6, B is 3. Again, I insist that you state whose A and B is at each line of GCD. Do not get confused, which is the one before. Also, the TAs not get confused. 6 is 3 times 2 plus 0. So the quotient is 2. Remainder is 0. I have now a stop. Why do I have stop? Because R is 0. Actually, let me write it inside here. Stop. Because R is 0. So who's the GCD? The last B. Which one is the last B? 3. GCD last B when R equals 0. You guys gonna need some practice with this. And we can also try to prove this theorem. So now we go back to that theorem there. And we say proof of Euclid theorem. Not very formal, but good enough for mathematical understanding. What we want to do, sometimes I say we want, as in I don't prove that yet, but that's what I want to. We want the GCD of A and B to be the same as GCD and B and R. That is fundamental theorem of Euclid algorithm. If A equals BQ plus R. So I do the integer division, and Euclid theorem says that's the same as that. So here's what I'm going to do. I'm going to say, let's call this guy D and this guy, pick another letter, F. I'm going to say, I don't know if they're the same. I'm going to say D is the GCD between those two, and F is the GCD between those two. Okay? So what does it mean D is the GCD between A and B? It means D must divide, I mean, it's more than that, but one thing is the GCD is a factor, right? So it means he has to divide both. Divides A, and D has to divide B. And from here, I say D has to divide A minus BQ. Because it divides A, and it divides B, so that means divides BQ. If you don't like the word divide, you can say multiply. A is a multiple of D. BQ is a multiple of D. Their difference, remember the first theorem? If two things are both multiple of something, their differences. But who is A minus BQ? A minus BQ must be R. So that says D divides R. Now let's look at F. F is the GCD of B and R. That means F must divide B and F must divide R. So from those two things, I say F must divide BQ plus R, right? It divides R, it divides B, so must divide their sum, their linear sum. Doesn't matter who Q is, as long as Q is integer. Who's with me? But who is BQ plus R? A. So F must divide A. Now, if D divides R and D divides B, I knew that was written somewhere here. D is a common factor, right? Between B and R. It divides both of them. And there is a little lemma that you have to prove at home. It's in the notes. If I have a common factor between two things, that common factor is actually a factor of their GCD. Any factor between two numbers must divide their GCD. GCD is not just the largest divisor. It's the divisor that's a multiplying of all the other divisors. So that means D must divide the GCD of B and R. And similar for F. F is dividing B, so F must divide the GCD of A and B. So this one here, GCD on B and R, means that D divides F, and this one means F divides D. But the only way D divides F and F divides D is if F equals D. I know I went a little bit too fast, and I did that on purpose. Part of this course is that we have to be more fluent in proving things. Again, I'm not emphasizing the formalism here, but your speed at thinking. Okay, all this stuff here, while it's not very formal, it's actually 100% rigorous mathematics. It follows the lines of thinking, and you're going to need this kind of thinking. It's part of the requirements of this course. So that proves that GCD is the same as GCD, which is the theorem here. And because of this theorem, the algorithm works. We need to do one more thing today. That is to attack this problem of the inverse that we've been struggling for 2 lectures now. What is the inverse? And when the inverse exists, right? That's why we need to do the linear cipher decoding. So let's pick an n, at least 2, integer of course. Sometimes I write integer this way, like it belongs to z. And we know Zn then is 0, 1, 2, up to n. We have a new theorem. We pick an A Zn. And the question is, do we have an inverse? Right? That's what we've been looking at for the last 2 lectures. Is there an inverse or not? If there is, that inverse times A has to be 1 modulo n. Here's the theorem. There is an inverse if and only if what? Yes.
Is that greater than 2 or greater than equal to 0?
What? This n?
Yeah.
When we do modulo something, we do modulo something that's at least 2. We don't do modulo 1 and modulo 0. So when we pick an n as the base of like a numeration basis, we don't use 1 as a numeration base. It's 2, right? So when there is an inverse, anybody knows the answer? I think sometime last lecture somebody speculated.
Is it like if the GCD of A inverse E is A inverse and
No inverse. If the GCD between A and n
is equal to 1?
is equal to 1. Or,
Yeah.
in other words, they are relatively prime, also called same coprime. These names mean A and n have no common factors, right? That's what GCD equal 1 means. By definition, GCD is the product of common factors. 1 means there's no common factors, and that's exactly what we saw an hour ago. We could inverse that 5 modulo 26. Why? Because 5 and 26 do not have common factors. How about 4 and 26? Why there is no inverse of 4? Because 4 and 26 have common factors. So GCD, we could also say no common factors. Now, one implication of this theorem is obvious. So let's do the easy part, proof. If there is an inverse, this is a trivial proof. What does it mean? A times A minus 1 has to be 1. Right? That's what it means to be an inverse. Modulo n. I'm not always going to say modulo n because everything is modulo n. But then we have our first theorem that says, well, if that's true, then n has to divide A at A minus 1 minus 1. Right? It has to divide the difference between those two. Which is the same thing as saying A times A minus 1 has to be nk plus 1. Right? It's saying it's a multiple of n plus 1. That's why the remainder is 1. Now, can A and n have a prime factor in common? If A and n will have a prime factor in common, what will happen with that prime factor? Will have to be a factor of 1, right? A common prime, P that divides A and divides n, will imply from these 3 things, P has to divide 1. This is a contradiction. Right? If it divides this part and divides this part, we'll divide the difference, which is not possible for a prime to divide 1. That's the easy way. So if there is an inverse, so there is no prime, that means GCD of A and n must be 1. But what about the other way? That is, what's the other way? What's the backwards proof? This is a if and only if sign, so it means it has to work both ways. Both the implication and the converse are true. And this other way states what? If GCD of a and n is 1, then there must be an inverse. Right? It's the opposite of that. This one saying if there's an inverse, GCD is 1. This one saying if GCD is 1, there must be an inverse. Well, that's something the regular sections cannot prove, because they started on the wrong mathematical foot with things like GCD is the largest number and primes do something and that. And once you start with those things, boom, you can't make this proof. Okay? But we started on the right foot here. More expensive, as in more computation cycles for you guys to follow me. But because we did that, we can make this proof. So we know the GCD of A and N is 1. We need to prove that there is an inverse. Now, we don't necessarily need to find the inverse. We only need to prove that there is one. So here's what we're going to do. We're going to consider a very important set called PA, which we're going to deal for the next 2 weeks with, which is the powers of A modulo n. So literally, I mean A is a power, A squared is another power, A cubed is another power, A to 100, so on and so forth. All the powers. Those are modulo n. So I literally take A and write all the powers of A. Now, because this is modulo n, this set must be finite, right? Modulo n, there's only so many possibilities, right? How many possibilities are Zn? N. So when you write all this sequence of an infinite sequence, what needs to happen at some point? You can have an infinite sequence in a finite set of values. That means at some point, powers start repeating. Right? If I write an infinite sequence, A squared, A cubed, A fourth, A sixth, A8, on and on and on and on, but there's only a finite number of possibilities in Zn. Those powers must be repeating at some point. That means there is some power m that is the same as some hour power n, not n, let's say m and k, modulo n, right? That's what I mean. There's some two powers that actually is the same value modulo Zn. Who follow this thing? If this is called pigeonhole principle, right? If I have 6 boxes and I'm throwing in more than 6 objects, 2 objects must fall in the same box. We heard about principle before? So now I'm going to apply my first theorem. I'm going to say, n must divide their difference. So that means I'm going to take one of them common factor. So let's just say this is 1 and this is k minus m is a multiple n times something. Right? So I took common factor a at m, assuming m is smaller. I got a at m is n times s. So now I have n divides a at m times 1 minus a at k minus m. But n and a are, the GCD of those is 1. And like the prime, if n is coprime with something, like a at m, if it's coprime with a, it has to be coprime with a at any power. If there's no common factors between n and a, there's no common factors between n and any power of a, because prime factors cannot appear out of the sudden in a at m. All the prime factors here, where they're coming from? From a. So if n and a don't have any common primes, n and a to the m have no common primes. So if there's no common primes with this factor, n has to be dividing this other factor. N has to be divided a k minus m minus 1. So I just found the power v, let's say v is k minus m, and I found the power a at v equal 1. V is called the order of A is a power A at V equal 1. I just found the inverse. What is the inverse? If A at V is 1, what is the inverse of A? If I tell you 11 at power 121 is 1 modulo n, 201, what is the inverse of 11? If 11 at 1201 is 1, A times what is now 1? If A at V is 1, what do I need to put here?
A, it's a B minus 1.
Very good. A at V minus 1 is now the inverse of A. We need to revisit this proof. I know this is now jumping way into the college realm. In fact, the regular sections don't even do this, okay? So now we're not at the high school anymore. So we're going to do this proof again, and we need to sleep on it. If I found the order is at what power gives me 1. I also found the inverse. B minus 1 gives me the inverse. If you have recitations, don't forget there is a quiz. Quiz is the beginning of the recitation, and we have all these answers posted if you want to check them out. Can I have the attendance sheet, please?
It's right on the.